Hello everyone, I'm Tarun. So in today's talk, we'll talk about the soft memory limit in Go 1.19. I know I only have 7 minutes, but I'd like to first thank the organizers for the awesome conference here we have today. With that, let's get into the talk because we only have 6:45. So I'm Tarun. I'm an engineer at Gitpod. Before that, I was a maintainer of the open source project called Linkerd, which is a CNCF incubated service mesh project. Apart from work, I try to run every now and then, and also I like coffee, like I'm sure a lot of people here, and you can find me at those IDs. So now, first of all, full disclaimer ahead, we have a very nuanced topic here. To make it easier to understand, I had to remove some variables from the formula and stuff like that, but you'll get the macro overview of what you're talking about. Now, so obviously, Go has a garbage collector, which means every time we allocate some memory, every now and then the garbage collector goes forward, clears the clears the memory that was allocated in the heap, which is unused anymore, which means every time the GC cycle has two parts to it, right? The mark and the sweep. First, the memory is marked and then it is swept. It is made available for newer allocations. So now the main question is, when do you trigger a GC cycle, right? Because that makes all the difference. Now, uh, GC, GC cycle is triggered whenever the memory reaches a certain target, and that target is calculated every time a GC cycle is already run. So yeah, so once a GC cycle happens, the next target is calculated, and then during that target we run the GC. So the target is essentially the alive heap, the current alive memory plus alive heap into GOGC, which we'll talk about by 100. So leaving the alive heap, we have two more. We have one variable, right? That is GOGC. By default, the GOGC value is 100, and if we substitute that, we essentially get target equal to 2 into live heap, which means we run the GC every time the memory doubles in the default case. Yep. So, and if you look at the graph here, so every time we go from 20, so first this is an application that grows like steadily, right? It could be, it is a service that handles incoming requests, and every time for a request we allocate some memory, do some work, and then end with that. So as you can see here, every time we go from 20 to 40, a GC cycle is run, the memory is cleared, and we are back again. And that happens in the fall. That happens. And then, but as you know, your GoGC is configurable, right? You can increase GoGC. So now, if you set your GoGC to 200, which means the target now we'll be waiting more time until we run the GC. So which means the GC runs a bit later, which means lower GC CPU times, right? Because we are not running the GC as frequently. But the trade-off is the higher heap overhead, right? Which means we are running at a later point than usual, which means higher memory usage for our Go applications. And the other side is you can decrease Go GC, uh, which means the target memory is lower, which means the GC runs earlier than required. Which means the CPU time is a lot higher, right? Because we are running a lot more frequently. But the heap overhead is lower here, right? Maybe in some constant environments, you would need that to happen to run to have the Go GC run more frequently. This is all well and good, and it was the case until the 1.19. But then there's this case of transient spikes and limited memory, right? So now imagine the same application. Now there are sudden spikes to our service, which do happen, right? And then our memory usage like shot up from 20 to 30 as a default. Now for a GoGC value of 100, the target is 60 MB, right? But your application could be in an environment where 60 MB is the limit. Yeah, so for example, your application is inside a container which is running on Kubernetes, and you have a memory limit of 60 MB, right? Which means the application is probably going to be marked out of memory uh, if the GC cycle is not run earlier. And the other crazy aspect to this is the fact that when you go from now imagine a case where uh, the peak usage is something around like 40 MB. Your GoGC is 100, and you are at a 60 MB limited environment. Uh, because of the peak case, you can't really set a GoGC value higher than 100, because if you do that in the peak case, your application will be out of memory. So there's this whole aspect of that the user has to configure to fire to so as a user you have to keep the extreme case in the mind, like the peak memo, like like the transient spikes to actually set the GOGC value. And as you all know, transient spikes are transient. You can't really like expect them to be at a certain point at a certain value and things like that. They're very rare and we can't really estimate how that would be. So that's where the go mem limit comes in, right? It's a configuration variable through which you can set an upper limit on the GC target. So which the go mem limit includes both heap and non-heap overhead. So this means now the target heap is the minimum of go mem limit and the go GC target. So this means now in the previous case, right? In the 30 to 60 example, if you have an go mem limit of 60 MB, you'll not shoot your target will never be 80 MB, right? Like the case we discussed it a lot. The GC cycle would be triggered at 60 MB, like you'd want to not have your application out of memory. But the clause here is that we can't really take like go mem limit directly, because go memory limit the environment variable includes both heap and non-heap overhead. But the GC only concerns itself with the heap overhead, right? So there is the go runtime and all the other memory that is also used. So this value essentially becomes minimum of go mem limit minus non-heap overhead. So we are specific to the heap overhead, comma the GoGC target memory that we calculate through the GoGC value. This way, we are always falling back to the minimum if you have a target higher than that, which could be the case in transient spikes and things like that. So that's how go mem limit works. And thanks for listening to the talk.